And here we perform bioinspiration because in natural systems, there are actually lots of examples where we can get inspiration from birds or flocking behaviors of different types of animals. Now, in our case, we want to transport a load using multiple robots. So, in case of ants, actually, it's even better. See here, the ants are carrying the lizard, and they're traversing on rough terrain, pretty much what we have to do on Mars. And see, there are actually lots of supporting ants, which are always around, and they're looking what's going on, and then they're probably asking the ants that, okay, are you tired? Can I replace you? And so on. So, and also they are avoiding the harder routes and going towards easier routes. So, inspired by this, we designed our simulation for obstacle avoidance and then carrying a load. So here, this is the first part where we balance the load or payload using the robots. So these tiny little ones are the robots, and these are the load share for that specific robot. So using Voronoi tessellation, we actually try to, like for this picture, how this robot should move. It should move in a direction where it can actually reduce the load share of this robot. Otherwise, this robot will complain and it will become really tired. And that robot doesn't have number 3 too much of load, so it will move away from number 3 and towards number 4. And this is the flow chart for the overall thing, and I think we can skip that and go to the simulation. This was done in Repast Symphony Multi-Agent Systems simulation software. Okay, so they're performing the load balance, and there are robots carrying, and there is supporting agent like the ants, and these yellow ones are the obstacles. And as they become darker, that means they're dying, so they're running out of power. So when they totally die, they will become red, and the replacement will come in. So they're doing the load balancing again, and one of them is already dead, the second one is dead. Can they reach? The goal is in the right top corner. How many of you saying that they can reach? Oh, great. Optimists. Okay, just 2 of them left. Almost there, but oh no, now actually 2. And they become so dark because they don't have energy. Just 1. Actually, they could reach there. So in many cases, they don't when they are they run out of the power. So we ran the simulation over and over for several times, and for different number of robots inside the system, and with supporting agents like the ants, or without the supporting agents. And we found that, as it should be, with increased number of obstacles, their success rate actually goes down. And with increased number of robots, also the completed distance is more. And in case of with or without supporting agents, it actually doesn't vary that much in terms of this success rate, but they vary in energy curve. So this is the energy curve, but this is the case where the visibility range for each of the robots is changed. So for visibility range 3, which is the dotted line, the first robot dies earlier because they have problems in load balancing in the beginning. So if they have too much of high load on one robot, that actually runs out of power faster compared to the other robots. So from this cooperative load transport simulation, we can gradually go towards real application for this on real robots, but there are lots of challenges we have to overcome, like the load balance is performed assuming that the load is not toppling from the robots. And also, we assume the flat terrain, but in terms of real application, we have to go to the rough terrains. So that was in terms of the obstacle avoidance. In many cases, you cannot avoid the obstacle. Like this place in Mars, this again Curiosity rover's picture, is called Dingo Gap. I don't know why they named it like this, but this is the place where avoidable obstacles are there, but here it's very difficult. You have to go through all those. And we come up with a theory inspired by the motion of the liquids, that if there are two potholes and if you fill in one with water or other liquids, and then if you add more liquid, it actually gradually flows to the next stage. So we can possibly perform the same using robots. So the robots, like the yellow robots, they can go and then build platforms, and then the green ones, they fill in this gap so that the yellow ones can again pass over this easily, spending less energy, and gradually actually going towards the next stage, and so on. Now for this, we propose a design of a robot which has actually two square-shaped wheels and two connector mechanisms, plus an inertia drive block. If you see this picture, this is a work done in MIT on a modular robot called M-Blocks. So we're planning to use that technology in this robot, plus add a couple more wheels so that the robots can be more controlled in their locomotion. It's a work by Dr. Detweiler's advisor, Dan Miller. So just like those robots, it's possible to use that drive, inertia drive, to create impulse and then move around like this. But this is only when the robots are aligned together. In some cases they might not, especially for rough terrain cases. The robot might be like misaligned, like in a higher position or lower position, and using the wheel actually they can align and they can use the magnet to connect with each other. And then they can probably use the inertia drive. So this work proposed a theory for locomotion on rough terrains while traversing the obstacles and so on, plus a design for a robot which can be possibly used in this system. So a combination of the two, theory and then the design of the robot, can possibly find like real robots which are traversing over obstacles rough like that. So to conclude the dissertation, in this dissertation, like two main categories of contributions were made. Like one was in the fields of modular robots. We have developed a novel modular robot with 4 degrees of freedom and docking mechanism which is self-healing capable, and Moderate 2, which is another modular robot for rough terrain traversal capability, and the other one that I just showed, Mamur. And in the field of planetary exploration, we have performed actually a lot of study in the field of sustainability in a planetary exploration case. With that, I'd like to give the references, additional references that I used in this. And I thank my committee. They were really supportive, and then it's really good that all of them are pretty much closely related with my project, because all of them have very good experiences in the pretty much similar field. And NASA Nebraska Space Grant and NASA EPSCoR, they provided the funding. And my home country, Bangladesh, especially for providing me almost free quality engineering education. And Nebraska and the United States for giving me the opportunity to take me where I am now. There are some specific contributions from Janping, who did the simulations, like the robots in group. Dr. Lin Ketso in the middle, in the computer science department, he gave some good feedback in this project. And Ching, she gave some good literature review on the behavioral, cooperative behavior of the different animals. Andrew is here. Andrew helped me with the obstacle traversal problem. And I thank all my friends and family in home and abroad. And Dr. Nelson's Random Lab. Do you like the logo? Kind of. Okay. So our lab is called Random Lab. So I thank all the members of Random Lab for being supportive. And Cementing Lab is Dr. Dasgupta's lab in UNO. Especially Hossain. He helped a lot in this project. And here's a logo, Google. Yeah, I really wanted to give thanks to Google because without Google, I can